So today I just want to look at standard deviation, but more the notation of standard deviation. So let's full screen. All right. So the standard deviation is a quantity calculated to indicate the extent of deviation for a group as a whole. So we have a whole lot of data, and so that's our group as a whole. And the standard deviation is this quantity that we calculate, so a value, and it gives us some sort of indication of how deviated all the data is from one another. So the main thing I want to go over here is notation. But before we do that, as we know, we have a population, that's all the data. And then of course we have a sample. So just a selection of points or data values from that entire population of data values. So as a result, we're going to have a population standard deviation and a sample standard deviation. Okay, so again, remember little n denotes the sample size, capital N denotes the population size. So notation-wise, the population standard deviation is denoted by this Greek letter sigma. Sigma. All right. And then the sample standard deviation is denoted by our regular letter S. So if we go back to our population standard deviation, it's the square root of all this stuff underneath the square root. So what does all that mean? So that's what we want to look at and try to decipher. Okay, so in the bottom, we have a capital N. So that's a population size. Okay, good. In the numerator, we have these various symbols. So before we get to the ones we don't know, let's look at the ones we do know. So this one right here, the mu, that's the population mean. Okay, so now xi, let me see if I have room for that. That represents the value of the ith data point. So value of I data point. So the value of the data in position I. Okay, so for example, if I equaled 1, then it would be the data value in position 1. If I was capital N, then it'd be the value of the data point in the capital Nth position, so the last data point, and so forth. Okay, so, and then if you notice in brackets, what is that value? So xi minus mu, that's the population deviation. Population deviation. For I data point. All right, and notice we square that value. So far, we actually know quite a lot. The one part that might be new for most people is that part. So let's have a look at that. I'm just going to scroll down a little bit. So let's look at what this means. What is that? All right, so that can be, okay, so let's look at that. So this, I'll pick another color so we don't get confused. So this symbol here, that's a Greek letter, it's called sigma, but it's capital sigma. So it's the capital, like the capital of this value. So this is capital sigma, let's put it that way. Capital sigma. This is lowercase sigma. Okay. So what sigma represents in math? It represents sum. All right. So sum of what? All right, so we have at the bottom of the sigma, we have I equals 1, and at the top of the sigma, we have a capital N. So this is a sum of something from I equals 1 to I equals capital N. That's what this means. But of what? So if we were to put, this is just an example, let's erase that and let's instead put AI. So AI represents some values. So AI represents the ith value, of a sequence of values, of a sequence of values. What does this sequence look like? All right. Well, in this particular case, let's make this a little smaller. This case, our sequence looks like AI. So the A1, A2, A3, A4, all the way up to AN. So our sequence, of values this is our sequence. So this sum, this purple capital sigma, it's telling us, take the sum or add up all the values in the sequence, and the sequence is represented by this A sub I. So in other words, we're going to add them all up. In other words, we have A1 plus A2 plus A3 plus A4 plus all the way up to A capital N. So this can be represented in shorthand by this big capital sigma, and A sub I, and then below the capital sigma is I equals 1, and then on top of the capital sigma is N. So I equals 1, so that's where you start counting or you start your sequence, and the capital N on top, that's where you stop your sequence. This A sub I represents the values in the sequence, and the summation represents that you need to add all those values in the sequence. So just to review that. Oh, all right, so let's just scroll back up. Let's review. So we have sigma I equals 1 to capital N. Not sure what's syncing here. Okay, I guess it's synced. All right. It's sigma, capital sigma, I equals 1 to N of x sub I minus mu. We square that and then divide by capital N, and that then we take the square root of that, and that equals our little sigma. So this is called our population standard deviation. This is our population standard deviation. All right. Okay, so let's go back up. And our sample standard deviation, let's look at that formula. Again, very similar. So in this case, well, let's pick another color so we don't get confused. This is our sample mean now. Right, X bar represents our sample mean. We now have little n, which is a sample size. Remember, our sample is going to be smaller than our population. Our x sub I is again the value of the ith data point. We're taking the sum from I equals 1. The first value that we're adding up occurs when I equals 1 in position 1, all the way up to position little n of the square of the deviation. So this x sub I, the value of the ith data point, minus the sample mean, that's our sample deviation. And we're squaring all those, adding them up, and then dividing by n minus 1. So 1 less than the sample size. And then we take the square root of that. Now, why do we divide by little n minus 1 when we're considering the sample standard deviation? So let's look at the note. So the note says that n minus 1 is in the sample standard deviation. So we use n minus 1 in the sample standard deviation formula because when a sample is taken from a population, the sample tends to underestimate the deviations in the population. So that's why we use n minus 1 rather than capital N, because there's like this underestimation of the deviations. So the deviations are most likely larger, but when you take that sample, you end up with a smaller deviation than you would have in the entire population. Okay, so hopefully this helped with regards to notation, because it can get confusing. Let's clean this up. All right, so it's a bit messy, but we have our standard deviation. The standard deviation is a quantity calculated to indicate the extent of deviation for a group as a whole. We have a population standard deviation and a sample standard deviation. So recall, lowercase n represents sample size, uppercase n represents population size. Our population standard deviation is represented by the Greek letter lowercase sigma. The sample standard deviation is represented by the lowercase s. And if you look at the formula for the population standard deviation, we have mu, which is our population mean. We have x sub I, which is value of the ith data point. We have our population size. If you notice, x minus xi minus mu is actually our population deviation for the ith data point. We take the deviations of each data point, square that value, that deviation, add them all up. That's what this notation here means. We add up all those squares divided by the population size and then take the square root, and that gives us our population standard deviation. The sample standard deviation is very similar, except we use the sample mean. We end up calculating the sample deviation for each data point in our data set. We square all those sample deviations and we add them all up, and then we divide by n minus 1. So the sample size minus 1, and that's because when we take a sample from a population, the sample tends to underestimate the deviations in the population, so this corrects for that. So I hope that helped a little bit with notation for the standard deviations. And there'll be another video on how to calculate the standard deviation using some of the functions in Excel. Thank you.